All right, so the next topic we're going to talk about are parametric equations and plane curves. Up to this point, when we've looked at an equation, we've looked at an equation in terms of x and y. And so we would say, here's the graph of some equation in the xy plane. Okay. This graph is an upside down parabola, so let's say it's this y equals negative x squared, maybe something like that. And we could say that this is a way to describe a particular situation. Let's say an object is propelled into the air at an angle of 45 degrees. So let's say you're like throwing a baseball at an angle of 45 degrees. You throw it up in the air, it goes up, and it comes back down. Okay? And that equation, which is graphed this way, could describe that situation. All right. But the problem is that doesn't necessarily tell the whole story. And so when we're looking at a particular situation like this, we might say, all right, if this was, say, an object propelled in the air or a baseball thrown in the air, whatever, this tells us the path that that ball traveled on. So it basically looks at what happened after the fact. It said, okay, this happened, and this describes what happened. But we might want to look at it in a little bit more detail and say, when the ball was right here, what point in time was it? How long did it take for the ball to go from here to here? What point in time did the ball hit the maximum point? When? When was it right there? Okay? When was it right there? Well, in order to answer that part of it, we need another variable. Another thing we could say is by looking at this graph, when you typically draw the graph of a xy equation, you see the arrows on either side, right? It looks like that. So it's pointing down, it's pointing down. What direction did you throw the ball? How do I know I started here and the ball was traveling this way? Okay. Again, all that stuff is missing if you just look at this xy equation. So if we introduce a third variable, let's call that variable t and have that variable represent time. And let's have x and y be dependent on that variable t. So this point, which has an x and a y coordinate, is actually has each of those coordinates is dependent on this variable t. Then what we can do is we can use that variable t to answer a lot of the questions that I just posed to you. And so that's the idea of parametric equations. So if a particle is moving along a curve C in the plane, we can describe that particle's motion by satisfying its coordinates as a function of time. So x is a function of t, y is a function of t. And so, in other words, at time t, the particle is located at this point f of t, g of t, and the curve C is described by those two functions of t. You could break it out as two separate equations. You could put it together as coordinates of an ordered point. But nonetheless, this is the idea of parametric equations. And this first set of equations that we have here is what we call the set of parametric equations. And the curve that is drawn is called the parametric or plane curve. Okay? So we refer to this C of t as a parametrization with the parameter t, or whatever parameter we call it. We don't have to use t all the time, but parameter t. And with x and y being functions of t, we could either write this as C of t equals f of t, g of t, or just simply f of t, g of t. And so the idea is, instead of having this single equation that has y equals f of x, so this y and x equation, we could have these two separate equations describe the exact same thing by introducing this new variable. And so, say this curve that we have right here can be drawn using an xy equation. But we could draw that same curve using this set of parametric equations, okay, and get that additional information. What are we going to get? where the particle is at any particular time t, then in that case, as t moves forward, we would get the direction of the curve as we move through. And we can also create some pretty complicated curves by having this new variable as well, that maybe we couldn't necessarily do with just x and y. All right, so let's start with a pretty easy example as to how we would go about graphing a set of parametric equations for a single plane curve. So if we want to sketch a parametric curve, one way we can do is just hand plot it. You've done an XY table before, where you pick some x's and get the corresponding y's. What we're going to do is we're going to create an x, y, t table. So we're going to pick some random values of t. We're going to plug them in to the x equation and the y equation for t and find out what the corresponding x and y's are for that given value of t. What we'll then do is we'll plot those points in order of increasing value of t and trace out the curve. And that's going to give us a specific direction, which will give us the orientation of the curve. So again, this is a pretty easy example. So let's sketch the curve with the parametric equations x equals 2t minus 4 and y equals 3 plus t squared. So these are how I define my x and how I find my y. I use random values of t. Okay, there's no real reason why I chose these. I like some negative, 0, some positive. Okay, so I pick a value of t, plug it in here, I get an x. Plug that same value of t in here, I get a y. There's one point on the parametric equations. Then plug another x value of t in, you get an x, you get a y. Another value of t, get an x, get a y. Another value of t, get an x, get a y. Okay? And so what's going to happen is we're going to plot these points. So negative 8, 7 would be, say, here. Negative 4, 3 would be here. 0, 7 would be here. 4, 19 would be here. If we had some other negative values, say, I don't know, negative 3 for t, whatever, I could get all sorts of points. Okay, the more points you have, the better. But what happens is that these points are going to trace out this curve. You see it has this parabola shape. We also see that it's going in this direction. Okay, so the parametric curve for this set of parametric equations can be graphed like this. So we have this curve in this direction. Notice, again, this is being graphed on the xy plane. Okay, and same as we would with an xy equation, a y equals f of x equation, okay, would be graphed on this xy plane as well. But what we're getting is this curve in a particular direction with all this additional information that we wouldn't get from this y equals f of x equation. And this is the purpose of parametric equations. But to graph them, it's fairly simple to do with a table. Now, obviously, if you have a more complicated graph, okay, this is going to be harder to do. Your table is going to have to be a lot bigger. You're going to have to choose a lot more t values to try and get an idea of what the graph will look like. Another way to look at what the graph of a set of parametric equations would do would be to combine these two equations into a single x and y equation and to graph it using all the things you've learned through algebra up to this point. And so we'll do that with this exact same equation. Remember, x was defined as 2t minus 4, y was defined as 3 plus t squared. What we want to do is we want to combine those two separate equations, those two separate functions of t that describe x and y, into a single x and y equation so that we could look at possibly graphing it or describe what curve would represent that set of parametric equations in the xy plane, etc. And one way to do this is through a process of eliminating the parameter, eliminating the t value. Okay? And so let's look at how we do that. So one way to do that is by simply looking at this as almost as a system of equations. So we have x equals 2t minus 4 and y equals 3 plus t squared. So what I could do is I can take one of these two equations and solve it for t. This one's pretty easy to solve for t, so I'll do that. So if you look at this, this will be x plus 4 over 2 equals t. And then what I can do is I can take that and I can plug it in there into the other equation for t, in which case I'll have then an equation with x and y in it. So I'll have y equals 3 plus x plus 4 over 2. So there's my x and y equation. Now, okay, squared. Okay. Now, obviously, I would want to simplify this so it looks better, but nonetheless, that's my equation. I could do it a couple of ways. One thing I could do is I could say, all right, well, let's write this as y equals, if I square the numerator and denominator, I'd have x plus 4 squared over 4 plus 3. And I could leave it like that, very well, leave it like that, because you could graph this pretty easily in that if you think about this equation, it's a translation form equation. I could also write it as 1/4 x plus 4 squared plus 3. You want to just write it like that, whatever. But the idea here is I have a quadratic, plus 4 on the inside, plus 3 on the outside. What is this telling me? This tells me that I'm going to move 4 units to the left, and this tells me I'm going to use 3 units up. This 1/4 means I'm going to compress by 1/4, and I'm going to have a parabola as my shape. If you remember doing all this, you would have done this in algebra, okay, learning how to translate a parabola. If you don't like that, the other option would be to just multiply this out, and you would see you get a quadratic. But nonetheless, either way, we could draw the graph of this thing. You know, I like the translation form the best. So it's a parabola, 4 units to the left, 3 units up, and it looks like this, which is the same exact picture we had just a second ago when we looked at the t, x, y table to graph this. The difference is I don't have as much detail in this x and y equation as I had in the set of parametric equations, x equals a function of t, y equals a function of t. But I do get the same exact parabola. Okay, so let's look at some fairly common parametrizations. One of the most common parametrizations you deal with would be lines. Another one would be circles. So let's look at lines first. So, parametrization of a line. We know that the standard equation of a line is ax plus by equals c, or y equals mx plus b is slope-intercept form of a line. So if you're going to do it in terms of x and y, we know how to do all that. But let's look at it in terms of parametrization. So let's say we have a line that goes through some point P at AB, okay, and has a slope of m. Okay? To parametrize that line, we could write the two separate equations, x equals a plus rt and y equals b plus st, where t can go anywhere from negative infinity to positive infinity. And r and s are found such that m is equal to s over r. Okay? R can't be 0. Otherwise, this denominator would be 0 and the slope would be undefined. So, let's look at an example. Find the parametric equations for the line through 3, negative 1, and with a slope of 4. Well, one way we can write 4 is we can write 4 as 4 over 1. Or we could write it a bunch of other ways, right? We can write it as 8 over 2, etc. But let's just usually keep it in simplest form. So let's go with 4 over 1. So this is your A, this is your B. According to this, S would be 4, R would be 1. So the parametrization would be X equals A plus RT, so just 1 times T, and Y equals B plus ST. And that's it. That's the set of parametric equations that would describe this line. We could also use our point-slope formula to write the xy equation that describes this line. It's not what it asked for in this problem, but you could easily do it. You know, our point-slope form, our slope-intercept formula, y minus y1 equals m times x minus x1. And so we could say y plus 1 equals 4 times x minus 3. And then we could simplify that more. I'm not going to do that because it wasn't the point of the question, but nonetheless, there's your xy equation there's your parametric equations. So pretty easy, okay? But this is a fairly common one. Let's look at another one here. Let's find the parametric equations for the line through the points 1, 2, and negative 5, 3. Now, what's missing here is the slope, right? You need a point and the slope to be able to use this. They didn't give us the slope, but they gave us 2 points in which we could find the slope. So m is going to be y2 minus y1 over x2 minus x1. So y2, let's just call this point 1 and point 2. So y2 is 3, y1 is 2, and then negative 5 minus 1. And so we're going to get 1 over negative 6. So there's your slope. So in this case, we can say that's S. There's R. Okay. And if we have that, now we choose one of these 2 points. It doesn't matter which one we choose. Our equation may look a little different if we choose one or the other, but still the same set of parametric equations for the same line. So let's just choose this first point. So x equals 1 minus 6t, and y equals 2 plus 1t. And there's your set of parametric equations that would describe the line that goes through these 2 points. Again, pretty easy, okay? And lines should be easy. But nonetheless, that's the set of parametric equations. That's how you can parametrize a line in 2D space. So another very common parametrization is a circle. So here we have a circle. Circles are usually dependent on a radius and a center. So let's say we have a radius R and a center, say AB. And we want the circle to be oriented counterclockwise. All right. Typically, when you deal with trigonometry and circles, everything's going counterclockwise. As the positive orientation is typically what you think of. And so x equals a plus r cosine t, and y equals b plus r sine theta. T theta, it actually doesn't matter what variable you use. Typically, when we talk about circles, we're talking about it being dependent on an angle instead of dependent on t. But this very easily could be a t here and a t here. And we could get this done just as well. So in this case, also remember that theta would have to vary between 0 and 2 pi. We're actually going to use a half open interval between 0 and 2 pi, which basically means we're going to include one of the endpoints and not the other, because 0 and 2 pi essentially amount to the same location as far as points go, as far as your angles go. So we don't need both of them. We would be redundant if we used both of them, but it's not that big a deal. So you think about kind of a circle. It could be centered here. It could be centered here. It doesn't really matter where the center is. If it's centered at the origin, A and B would both be 0, and we just have r cosine theta, r sine theta. If it's centered off the origin, then your A and B would affect that center, and you have A, r cosine theta, B plus r sine theta. We also could talk about an ellipse. So an ellipse, the difference between an ellipse and a circle is the radius, in which case a circle is the same radius all the way around. If we dealt with an ellipse, okay, which looks more like that, we have a center and we have 2 different radii. We have a radius in the x direction and a radius in the y direction. So we call this r, we call this s, and in which case then we just change this to r and s here, but it still has the same general setup. We'll just primarily focus on circles, but if we want to do an ellipse, since they're not too different, I figured it wouldn't be bad to sort of throw an ellipse in here as well and see how that's done. Okay, so here we want to sketch the curve represented by x equals 3 cosine theta, y equals 3 sine theta, where x goes between 0 and 2 pi. Then after we do that, we're going to eliminate the parameter and find the corresponding rectangular equation, the xy equation, that these 2 set of parametric equations could give us. All right, so looking at these equations and looking at what we know to be the set of parametric equations for a circle, where x equals a plus r cosine theta and y equals b plus r sine theta, we can see that in this case, here and here, that a equals 0 and b equals 0. So my center is 0, 0. And in both cases, r is 3. So if my radius is 3 and my center is 0, 0, that should be very easy to draw the graph. So 0, 0, go 3 units in all directions. And there's your circle. Okay? It's also going to be oriented, remember, counterclockwise. We could also plot points on this circle by doing the same thing we did before with the line and make a table. We could have a theta, x, y table where we plug a particular theta value in, say 0 or pi or 2 pi or whatever, and we get a particular point. So let's just look at one of these. We plug in 0 as my angle theta. So you know an angle 0 is right here. Okay. The point we would get for that angle would be, if you plug 0 in, you get cosine of 0, which is 1, so times 3, and sine of 0, which is 0, times 3, and you get the point 3, 0, which is exactly this point right here, 3, 0. Okay? And we could keep doing this, and we could get this point, and this point, and this point for these different angles that are rotating around that these points are dependent on. Not necessarily this is enough that we can draw the graph of this circle pretty easily, knowing the standard set of parametric equations that would give us a circle. All right. Next, what we want to do is come up with the corresponding rectangular equation. So one way to eliminate the parameter based off of what we've done before is to plug one of these equations into the other. But there are other ways to do it as well. Another thing we can do is use some trig identities here. We have one, and it's that cosine squared theta plus sine squared theta equals 1. Pythagorean identity. And it's an equation that relates sine and cosine together. Well, we can take these two equations and we can look at this first one and say x over 3 equals cosine theta. So we could just write this as x over 3 squared. Take the cosine theta out, replace it with x over 3. We can do the same thing here. Y over 3 is equal to sine theta, so y over 3 squared. And here we go. There's a rectangular equation. I could write this as x squared over 9 plus y squared over 9 equals 1, or I could write this as x squared plus y squared equals 9. You should look at this as your standard equation that you've had for circles in rectangular form since, algebra. And this would say, oh, it's a circle centered at 0, 0 with radius 3. Remember, this is always r squared. We have the standard x squared plus y squared equals r squared equation that we've used multiple times throughout algebra when it came to circles. And it's exactly the same thing that this set of parametric equations would give us. So they all connect together. The things you've learned before connect with this new set of parametric equation forms of circles. It's just parametric equations give us a little bit more information by introducing a new variable for which x and y are dependent on. There are tons of parametric equations. Here are two interesting parametric equations and their graphs, in which case you say x equals t minus sine t, y equals 1 minus cosine t. And what it describes is this. If you took a point on a circle, okay, say like a ball, and you rolled that ball this way, okay, this way, okay, and you just followed that point as it was traveling, okay, as that ball starts rolling this way, that point would essentially travel here, and then here, and then here, etc., and we would get, following that point on the ball or point on the wheel or whatever, you would see the path that that point would travel as it follows around the ball rotating. Okay, that's a pretty interesting one. This is a pretty crazy parametrization here. Very complicated set of equations, but it's a pretty interesting looking one. If you think about this, it looks like it might be 3 separate curves, but actually it's one curve. Okay, pick a starting point anywhere. Let's say it starts here, and you follow it around. If you start following it around, okay, what happens is it's going to continue to keep going around and around and around. Let's see here, and then I'm going to come in here, I'm going to come around here, and you see it just keeps traveling. I lost it somewhere along the way, but anyway, it's a single curve, okay? And it's going to be an infinite loop, and it's going to create this picture. Anyway, the point of me showing you this is that you can get some very, very complicated looking curves through a set of parametric equations by introducing this new variable. And you can call that variable t, you can call it theta, you really could call it whatever you want. Okay? We can then start to do calculus in parametric form instead of doing it in rectangular form. So we know that the set of parametric equations amounts to the exact same thing that the set of that the single rectangular equation would give us. One way to do this is to say, okay, then what's the slope? What's the change in y over the change in x? And we can do it by always converting back to the rectangular equation and doing everything we've learned already. But we can also leave those equations in their parametric form as the two separate equations and still do the things that we've talked about before. So how do you do that? Well, if you wanted to say find dy dx, you just do the derivative of y with respect to t divided by the derivative of x with respect to t. How is y changing over time? How is x changing over time? And do the two changes, dx dt, dy dt over dx dt. Okay, just make sure that dx dt doesn't equal 0. So pretty simple. So let's say we want to find the equation of the tangent line for a given curve. That curve is defined by these two set of parametric equations, x equals sine t and y equals cosine t. And we want to do it when t equals pi. So in order to write the equation of a tangent line, you need the slope of the tangent line and you need a point on the tangent line. Well, the point can be easily found by using that particular t and find the x and y point. So when t equals pi, x equals sine of pi, and y equals cosine of pi. Well, sine of pi would be 0, and cosine of pi would be -1. So my point that I'm going to find the tangent line at is 0, -1. But I also need to find the slope of the tangent line, which is dy dx. Well, based off of this formula, we could do the derivative of y with respect to t and the derivative of x with respect to t, divide them, and that'll give us what we want. Oh, so that's pretty easy. The derivative of this with respect to t, derivative of cosine would be negative sine t. Derivative of this with respect to t, so that would be cosine t. So there's your slope. We could also write that as negative tan t. If you want to use an identity, it doesn't matter. You could leave it as sine over cosine, but negative tan t. So then we want to find the slope of the tangent line at t equals pi. So if we're going to do that, we plug pi in here, so minus tan of pi. So you would have to know what the tangent of pi is. So the tangent of pi would be 0. And so if you look at that with a negative, it's still 0. So your slope is 0. And now you want to write the equation of the tangent line. So we'll use the point slope formula to do that. So y minus -1 equals 0 times x minus 0. So you see you just get y plus 1 equals 0. So y equals -1 is the equation of the tangent line to this set of parametric equations. Pretty simple. Okay.